Welcome back. Today we want to talk about the positive curvature case in the two-dimensional case, and we had done some preliminary work on that, and the point we were stuck on was the upper bound on the scalar curvature, despite having already the volume bound by rescaling. And I said that what we need is a Harnack inequality. So let me first do the Harnack inequality in the linear case. And then there is a famous theorem by Li and Yao, and this is the linear heat equation on manifolds. Suppose M and G is a compact Riemannian manifold, closed, no boundary, and with no negative Ricci curvature. And suppose we have a positive solution of the heat equation. In some time interval f greater than 0 satisfies dBT f equals Laplace f. Then we get that Laplacian of f minus the gradient of f squared over f, so we need the positivity, plus n over 2t times f is greater than or equal to 0. And notice that we have equality here on the heat kernel in Rn. So equality on the heat kernel. Now, and let me give a quick proof of this result. So the proof would be to look at the logarithm of the heat kernel. Let L be the log of f, and then we get dBT of L is equal to Laplacian of L, simple computation, I get Laplacian of f over f, and then you can write this as the Laplacian of log f plus the gradient of log f divided by f squared, which is the same as the gradient of L squared. And this, of course, relates back to the Laplacian of f divided by f. Let me see, it's Laplacian of f. Yes, right. And therefore, if we set the quantity q to be exactly the derivative of L minus d L squared, So then this just becomes a Laplacian of L, and the Laplacian of L is Laplacian of f minus the f squared divided by f squared. Okay? So we consider Q, and then we compute the evolution equation of Q. dt of Q. So we compute essentially the speed of the Laplacian of the logarithm. So we get ddt of Laplacian L, and since in this case the metric is not depending on time, we can commute ddt of Laplacian, so we get Laplacian of ddt of L, and ddt of L is over here, is the Laplacian of L plus gradient L squared. And now computing the Laplacian of this gives the Laplacian of Q on the one hand, since Q is Laplacian of L, so we get Laplacian of Q, then we get the Laplacian of dL squared. So when we compute the Laplacian of dL squared, we get on the one hand the Bochner term, 2 times the Hessian of L squared, and on the other hand we get 2 times the Laplacian of gradient L times gradient L. Okay? And now we have to commute on the right hand side the Laplacian with the gradient of L. So we get the Laplacian of Q, and then we get, if I commute here, I get the gradient of Laplacian of L, which is the gradient of Q, so I get 2 times the gradient of Q multiplied with the gradient of L. But then I made a mistake, so the mistake is exactly the Ricci curvature, so I get plus 2 times Rij times gradient IL gradient JL from the commutation of the Laplacian and the gradient. And from here I get twice the Hessian of L. But now I use the fact that I have non-negative Ricci, throw this term away, and I estimate this from below by the square of the trace. And so I get that this Q is bound, this is bound below by Q Laplacian plus 2 times the gradient term, plus, and this is bigger than 1 over n, we had this argument before, times the trace. But the trace of the Hessian of L is just the Laplacian of L. The Laplacian of L is Q. So we get Q squared on the right hand side. This is our ending point. ddt of Q is bigger than Laplacian Q plus gradient term of Q plus the square. But now we can use the comparison principle with the ODE, ddt of Q is bigger than 2 over n Q squared. And we know what that is. This is essentially minus 1 over t up to a constant. So just by the maximum principle, we conclude from here that Q must be bigger than minus n over 2t. And this, on the other hand, is the Laplacian of, where is it on the board? This is the Laplacian of L, which is df squared minus df squared over f, and this is the theorem. So this implies that Laplacian of f minus df squared over f plus n over 2t times f is greater than equal to 0, which is what we wanted to prove. Okay? So this is the inequality, and now the question is, what does it have to do with why is it called a Harnack inequality? And let me explain why this leads to a Harnack inequality. So as a corollary, I claim that we get a, let me just first give the computation, then formulate the corollary. So now consider two events, P1, T1, and P2, Q2 in space-time. P2, T2 in space-time, and the curve, and gamma, a curve from P1 to P2, also parameterized by time. And then we can compute the derivative of L along this curve gamma in terms of the partial derivative of L with respect to t, but then also with respect, we get an extra term where gradient L is differentiated by the chain rule in direction of the curve gamma. And now the LDT, it's still on the board, was our Q plus the LDT, the partial derivative. I should write here maybe, make this absolutely clear. The partial derivative of L is exactly given by our Q plus dl squared. So I can estimate this from below by Q, and the estimate on Q was minus n over t, so that we get minus n over 2t. And then we had the good term plus gradient L squared. And this term here I estimate by minus gradient L times gamma dot. Now the point is that this is quadratic in gradient L and this is linear, so I can further estimate this from below by minus n over 2t and put this in here, and then I'm left over with minus 1/4 gamma dot squared. And now integrating this from T1 to T2, I get let me write this like here. I get L at P2 T2 minus L at P1 T1 is bounded from below by minus n over 2, and now I can take here from integrating, I get the logarithm of T2 minus the logarithm of T1. I can write this as the logarithm of T2 divided by T1, and here I get minus the integral from T1 to T2 of gamma dot squared beta. But this, on the other hand, here this is the logarithm of r. So the difference, subtracting the two logarithms gives me the logarithm of the quotient between r at P2, T2 by r at P1, T1. And now, exponentiating everything, I can estimate from below the r at the later time in terms of r at the earlier time. So I get r at P2, T2, bounded from below by the scalar curve, by the, sorry, this is not r, I'm already getting ahead of myself, this is our function f. Positive solution of the heat equation at the later time is bounded below by the heat at the earlier time times, and then from here we get T1 over T2 because of the minus sign, and we get it to the power n over 2. And from here I get times e to the minus 1/4 times, and this is in Hamilton's notation, we call it delta over 4, where delta is the smallest possible value that you can get for this integral. So delta is the infimum over all these curves gamma of integral from T1 to T2 of gamma dot squared d tau. And this infimum, of course, is the best, is what you can do is take the geodesic, and then this becomes just the e to the minus 1/4 times distance squared divided by remaining time. So this becomes just this term here. This will become distance from P1 to P2 squared divided by T2 minus T1. And this is a Hanach inequality because it tells you how the temperature at a later time is bounded by the temperature at the earlier time. So notice that this is becoming a valuable estimate exactly when you have waited for a certain time. The solution must have existed for a certain time, so T1 has to be positive. And the other thing is, of course, that T2 cannot be too large because then the temperature would have cooled off too much. That's why you get the T2 in the denominator, and you get the best results if you have both T1 and T2 comparable, because then you have a constant bounded from below here. And this constant, of course, is controlled exactly when you are not too far away from the point P1. That's why you have the distance in here squared compared to the time. So if the time is comparable to distance squared, then you get a constant here, and you have a bound on this constant on the right-hand side, and you can compare the temperatures. That's the classic Hanach inequality, and of course this is sharp, as you see from this exponent on the heat column. Now, a couple of comments should be made. In Euclidean space, this can actually be made into a matrix inequality. So, remark this can be sharpened. And to say that the full Hessian of f minus the IF djf over f plus delta ij over 2t is greater or equal to 0, which you can also state as saying that the Hessian of the logarithm of the Hessian of the logarithm of f is greater than minus. There's an f missing here, and if you write it like this, you get that this is bigger than minus delta ij over 2t, which is of course the Hessian of the logarithm of the heat kernel. So you can write this also as saying that the I dj of the logarithm of f divided by the standard heat kernel is a convex function. So here rho is the standard heat kernel. And this fact, in turn, you can prove without using the maximum principle in Euclidean space, because obviously if this is true on the standard heat kernel, then the logarithm would be just 0 if you have f equal to rho. And from the representation formula, you know that any other positive solution of the heat equation can be written with the kernel rho as a superposition of other heat kernels at other points with positive weights, and the linear combination of any two positive log convex functions is log convex again, just by Schwarz inequality. So you can prove this result in Euclidean space by just using Schwarz inequality. Okay. Now, the point is that miraculously, almost exactly the same Harnack inequality that we have shown here for the linear heat equation also holds for the scalar curvature in two-dimensional Ricci flow. So now consider Ricci flow. We flow on sigma 2 gt with situation where scalar curvature is greater or equal to 0, and we have ddt of gij is equal to r minus r times gij, and we know already that in this case the scalar curvature satisfies ddt of r is equal to Laplace r plus r times r minus little r, where little r is a constant fixed in time given by the Gauss-Bonnet integral, the average of capital R. Now, the point here is that the scalar curvature satisfies exactly the same inequality. So theorem Hamilton in 1986, they proved that the Laplacian of the scalar curvature minus gradient r squared divided by r plus r squared plus r over t Did I get this right? Just a second. Plus r. Yeah, it's not r squared. It's r times r minus little r is greater or equal to 0. And it's not greater or equal to 0. Sorry, I forgot the important negative term. It's greater or equal to, this replaces the minus 1 over t term. So this is bigger than minus little r, which is a positive number, times e to the little rt divided by e to the rt minus 1. And of course, if t tends to 0, this tends to 1, so this is the 1 over t in the denominator that you would expect from the linear case. And note, in the unrescaled case, where ddt of gij is equal to minus 2 times the Ricci curvature, which is minus r times gij. So if you don't do the rescaling, then we get that Laplace r minus gradient r squared over r plus r squared plus r over, now we have n over 2, and n over 2 is 1, over t is greater or equal to 0. So this, up to this term here, this looks like exactly in the Euclidean space, in the linear case. So this is of course equivalent to that after rescaling. Now, how do you prove it? We can just follow the same recipe that of the proof that I showed in the linear case. You consider a quantity q which is related to the log of r. So proof, consider L is equal to the log of r, such that ddt of L is equal to the Laplacian of L, the Laplacian of L plus the L squared. This was the equation we get in the linear case. Now in this case, because of the evolution equation for r, which has this extra term, we get here, since we take the logarithm, the 1 over r disappears and we get this extra term in the evolution equation. So this is the only difference that we get from the linear case. And then we set q to be the quantity s in the linear case, the L dt minus the L squared. So in this case, this is now not Laplace L, but Laplace L plus r minus little r. So the same concept as in the linear case. And now you just compute, and the computation, is the same one. The only thing you have to now keep in mind that ddt of the Laplacian is not 0, you get an extra term. It's a good exercise. Follow the computation in the linear case and just watch out that ddt of Laplacian is not 0, but you have to differentiate the g upper ij, which gives you an extra term. But if you combine everything, you end up with ddt of q can be again bounded from below by Laplace q, same quantity as before, plus 2 times gradient L times gradient q, just as before. And then you get plus q squared and r times q. We get one extra term here, the little r times q. And where we used now not the Hessian squared of L bounded below, but you have to slightly adjust it because of this extra term. So you take minus 1/2 times r minus little r squared, and use the fact that this is now bigger than 1/2 times the trace of this squared, and the trace of this is just Laplacian L minus, oops, there's a GIJ missing, sorry. The trace is just Laplacian L minus r minus little r, which is Q. And now this should be little r minus capital R, so that what I'm saying is correct. And this, we use that this is bigger than 1/2 Q squared. And then you end up with this inequality, because by the way you had this twice, of course, from this Bochner identity. And once you have this inequality, you can just integrate. Notice that the solution of this ODE, the maximum principle, the solution of this ODE is exactly the quantity that I had claimed on the right hand side. So you get that Q is bigger than minus R times e to the RT divided by e to the RT minus 1. And that's the theorem. And now once you have the estimate on the Q, and therefore the estimate on ddt of the logarithm of R, you can now proceed just before and integrate everything up along a curve connecting two events in space-time. Right. Okay, so now consider again the curve gamma connecting P1, T1 to P2, T2 in space-time, and estimate ddt of L, which is again ddt of L plus the gradient of L times the tangential vector to the curve, now in space-time, and now in dl dt we had Laplacian L plus r minus r was Q, so we estimate Q from below and keep the dl squared, we combine this with this, so we get minus 1/4 gamma dot squared as before, and the other term coming from the Q was the term on the right hand side here, minus r e to the RT divided by e to the RT minus 1. Now notice that the numerator is the derivative of the denominator, so when we now integrate, we can get a logarithmic function on the right hand side again, so we conclude that L at P2, T2 minus L at P1, T1 is bounded from below by e to the minus delta on 4, where the delta is now defined again as the infimum over all gamma in space-time from T1 to T2 of gamma dot of tau squared, but this is now with respect to the metric at time tau. The metric is now changing in time, d tau. So I have this more complicated distance function between these two events, and from here this just gives minus the logarithm at the of this denominator at the later time, minus 1, divided at the e to the r at the earlier time, minus 1. And then we oops, this is not yet exponentiated again. I'm getting ahead of myself, so this is minus 1/4, exactly this delta over there. And now we exponentiate. And then on the left we have again the difference of two logarithms, and we conclude as a corollary here the Harnack inequality for the Ricci scalar. We get that the scalar curvature at the later time is at least as big as the scalar curvature at an earlier time, times e to the rt 1 minus 1 divided by e to the rt2 minus 1. And so again, we only get a result if we have some positive time t1, and if the time t2 is not too big, and then we get times e to the minus by 4, where this delta is defined like this one here. Okay, so now this is already nice because it says that if we are at a maximum point of the scalar curvature, it cannot fall off too much. Still, there's some work to do in order to control this delta. We have to show that in this time interval, distances have not deteriorated too much. And we still have to find an argument why this implies that the scalar curvature has actually a maximum for all time. Now, turns out that there is now something you can prove with the same estimate on Q as an integral estimate on the scalar curvature. Now, usually you would hope to get sort of a high P estimate on the scalar curvature. Turns out that's completely hopeless. You know, in some other theorems, you prove a higher P estimate and you use some Moser iteration, and then you get a super estimate of the quantity. Here, you want to just get a little bit better than the L1 norm. The L1 norm, you know, that's the Gauss-Bonnet integral. You know that's fixed. So Hamilton manages to improve that thing by just a logarithm. So here's the result. So consider the following quantity. Consider a function, a quantity that Hamilton calls z, and this is the integral of q. Q is the thing we just included, divided by times r is the rate, and we divide this by the integral of r d mu. Now integral r d mu is a constant because the area is a constant, and then this is the Gauss-Bonnet integral, so this is just a constant. There's now no time derivative. Just put it in order to see this sort of the average of q with respect to the measure r d mu. And the measure r d mu, we know, has the Gauss-Bonnet integral just depending on the genus. So this is a weighted integral of q with respect to this measure r d mu. And then we have the magical computation of ddt of z. This is because we don't have to differentiate this, we just put it at the bottom and just differentiate this with respect to time. So we get the integral of ddtq times r plus ddtr times q, and then we get from the measure, we get q times r times, and the measure, change of the measure is little r minus capital R d. And now inserting the inequality that we get for ddt of q in the last computation for the Harnack inequality, we estimate this from below, but 1 over integral r d mu times, and then here we had ddt, we can use the pointwise estimate because r is positive, so we get here r times, this was the Laplacian of q, plus 2 gradient L, the logarithm of r, times gradient of q. And then there was plus q squared, and then there was plus little r times q. And on the other hand, the next term gives us q times the Laplacian of r plus r times r minus little r, and then finally we have plus q times r times little r minus capital R. Notice here that this term here just cancels perfectly this term. And when we do the integration by parts on the Laplacian of q and the Laplacian of q, Laplacian of r there, then we see that this gives a minus gradient r times gradient q, just like this one gives a minus gradient r times gradient q. So we get minus 2 gradient q times gradient r. But here gradient L is just 1 over r times gradient r, because L is the logarithm of r, times r is also a gradient r. So this term here perfectly cancels both this and this term. So the only thing that we are left with is this term here and this term here. So we get ddt of z is bigger than 1 over integral r d mu times integral q squared times r d mu. And from here we get plus little r times qr over r d mu, but this is just z. And this is now the square of Q. So we can now use the Schwarz inequality, but with respect to the measure R d mu. And then this combines just to Z squared. So we get Z squared plus R times Z. And remember, R is a number which is positive. So now we get this magical ODE for ddt of Z, of this integral, is bigger than Z squared plus RZ. Now, if Z at any time, would be strictly positive, this term is positive, you can throw it away, then it would remain positive, and the Z squared term would make it blow up to infinity in finite time. But that cannot happen, because we have proven there is a solution for all time. We've already proven there's a smooth solution for all time. So it's completely impossible that this can blow up in finite time to infinity. So it can never happen that Z is going to be greater than 0. So we conclude from this, since we have solution is smooth on the whole time interval up to infinity, it follows that Z can never be bigger than 0. So we must have Z is less than 0 everywhere. Okay? So this integral QR is less than 0 everywhere. But what does that really mean? But the integral of Q times R in U, this was the integral of Q was equal to Laplace R over R plus R squared plus R squared plus, is that right? Laplace, no, it was multiplied with R, so it was the integral Laplace R plus minus gradient R squared over R plus R times R minus R d. And this is of course the same as the integral of minus gradient R squared over R plus the integral of R minus little r squared d. So our inequality here means that and this is less or equal to 0, so this means that we have a Poincaré type inequality r minus little r squared d mu must be less than integral of a gradient r squared over r d. We have this inequality. Right, and this now gives us the bound on the integral of r log r because of the following calculation. I guess I leave the Harnack inequality on the board. Because it's now rather quick. The next theorem says that integral r log r d mu is bounded by a constant less than infinity. And proof goes like this. We just compute ddt r of this, ddt of this thing, ddt of integral r log r d mu is, well, we get from the evolution equation of r, we get Laplace r plus r times r minus little r times log r. And then we get from the evolution equation of log r, we get 1 over r cancels this. So we get just Laplace r plus r times r minus r. And then from the d mu, we get plus r minus r times log r. And then we see that this is equal to we get the r minus r times log r cancels exactly this term. The Laplace r integrates out to 0, and the Laplace r times log r gets integrated by parts, so we get minus gradient r squared over r du from this term, and from this term here we get plus integral r minus r squared. But this is exactly what we just proved is less or equal to 0. So it means that this integral is bounded by its initial data. And this is a good point to interrupt.